So double angles formula, so that is we are going to evaluate a sine of 2 times some angle using 2 sine theta cosine theta. And well, so you might wonder where this formula might be coming from. Well, this is a result of breaking up. How about, okay, sine 2 theta can be rewritten as a sine sine theta plus another theta. And then, well, this is going to take us back to the previous section where we used the sum and difference formulas. Well, the first term is alpha, the second term is beta, but in this case, it turns out they're both the same. So that's going to be sine alpha, which is sine theta, times cosine beta, which is also theta, plus sine alpha, that's sine theta, cosine theta. And well, notice these are like terms, so this is simply 2 sine theta cosine theta. And that's where this double angle formula is coming from. Of course, you can derive the other two formulas the same way. For cosine 2 theta, break it up into a theta plus theta, and then use the sum and difference formulas for the cosine function. Now, one thing to notice here, check this out. Although we just have one alternative for the double angle for sine, we have three alternatives for evaluating cosine 2 theta. And well, these other two formulas are the result of replacing either cosine squared with the Pythagorean identity of 1 minus sine squared, or replacing the sine squared with 1 minus cosine squared. All right? So, and even though we have a formula for tangent 2 theta, well, of course, that can be derived using the formula we did last time to evaluate a tangent. And well, but I mean, for practical purposes, you can also do the following. Maybe simply sine 2 theta divided by cosine 2 theta. Either way should work the same. You should get the same result either way. How about we see these formulas in action with an example? So number one, let's see. We are given the value of a trigonometric function that is sine theta equals to 3 over 5. All right. So let's see. They're also giving us a condition here. Let me highlight the condition so we can interpret that condition. Well, what does that inequality, theta being greater than pi over 2 and theta smaller than pi, means? Well, this is just a fancy way to say that theta is in second quadrant. All right, that's all it is. All right. And well, how about we evaluate, okay, let me rewrite the function on the side. Sine theta equals 3 over 5. That's by definition, that's y over r, right? Because this point or this quotient of values may not be within the unit circle, so we need to be very careful about it. All right. So let's see. How about we use Pythagorean theorem, that is r squared equals x squared plus y squared. And r squared, that'll be 5 squared equals x squared, which we don't know, plus y squared, which is the 3 squared. That'll be, what's that, 25 equals x squared plus 9. And x squared equals to 16, where x equals plus or minus 4. Now we need to be very careful again. We have done this before. We need to be very careful with the sign that we take for the function, actually. I mean, for the value. Because in this case, we have a positive y. So since the point is in the second quadrant, that means r equals to, what's that? R equals to 5. And the point is sine, which is, or rather the y, which is 3. And in this case, well, if we take the number 4, since in this case we are in the second quadrant, that means we have to take the negative sign. All right? We need to go in accordance with the signs of the values in the Cartesian plane. And I think we have all the information that we need to get to evaluate these three function. So they're asking us to evaluate sine to theta, cosine to theta, and tangent to theta. The three of them. All right. What are we going to do to evaluate this? Well, so they're asking us to evaluate sine to theta. However, we're given sine theta, not the 2 theta. That's why we're doing these conversions or this information. And we're going to use the identities here to evaluate this function. So that's a 2 sine theta cosine theta. That's the identity for the double angle for sine. And all we have to do here is simply use the common ratios, that is 2 times sine. But sine is actually given, that's a 3/5. And cosine, which is defined as x over r, as opposed to y over r, which is the sine function. And in this case, x, which is -4 over 5. And we're ready to go. Let's just multiply across. 2 times 3, which is 6. 6 times 4 is 24 over 25. But we have a negative going on, so that's going to be its final answer. It's -24 over 25. All right. Yes?
Oh, I didn't know there was a quadrant 2.
Oh, it's this inequality here. In some cases, they will literally tell us, oh, if sine theta equals 3/5 in second quadrant, sometimes verbally, like literally, and sometimes in using this inequality notation. Because in this case, yes, this is pi over 2, that's a positive y-axis, and pi, so that covers the second quadrant. So that's inequality way to show it. What about cosine to theta? And again, here we have 3 options to evaluate this one. I'm just going to go with the first one. That is cosine squared minus sine squared. How about that? And we'll use the information about cosine and sine for this particular setting. And this will be, okay, cosine, which we got it to be -4 over 5 quantity squared, minus sine quantity squared, which is the number given. And just simplify this madness right here. All right? So that's going to be, negative square, careful, that becomes positive, 16 over 25, minus 3 squared, which is 9 over 25. 16 minus 9, isn't that 7, I believe? 7 over 25. And the good thing about these ones, well, we don't need to find a greatest, or rather a least common denominator to simplify. All right. How about tangent to theta? And again, although we have a formula for the double angle for tangent, well, sometimes it's okay to just go the practical way by simply using a quotient identity, that is sine to theta over cosine to theta. Okay, so sine to theta is -24 over 25. Divide that by 7 over 25. And while dividing by a fraction here, it's exactly the same as multiplying by the reciprocal. That is -24 over 25 times 25 over 7. And well, what's this? Divide out the 25s to leave us with -24 over 7. And that's final answer here. So again, it all stems again from going back to rewriting these trigonometric identities for double angles and the like in terms of trigonometric expressions of a single angle, and just given the information we get from the circle, I mean in this particular setting, not to be confused with the unit circle, because this is not a unit circle. All right, let's look at another example. How about we apply this to verifying identities? Well, hold on, let's check this out. I thought we were talking about double angle identities, and this is a triple angle. So, well, we're going to use a combination of double angle identities and the sum difference identities that we did last time in the previous section to come up with something of a triple angle. And we can use also this same idea for quadruple angles, quintuple angles, your favorite n-tuple angles, 17 theta if you want, 57 theta if you want. I mean, it's going to take forever, but I mean, it's doable by the way that we're going to do it here. All right, so we want to show that sine 3 theta, it's the same as saying 3 sine x minus 4 sine cubed theta. All right, let's go about it. So I would like to break up this sine of 3 theta like this. Sine of 2 theta plus theta. And we're going to go back to the formulas from back in the previous section when we had like, what was that? Sine of u plus v. That's sine u cosine v plus cosine u sine v. Let's apply this formula for this breakup to theta plus theta. All right, what's that going to be anyway? Well, let's think of our u to be the 2 theta and the v to be the theta. Oops, the v, not the theta. So, using this formula, sine u, that's a sine 2 theta cosine theta, and then plus, what's this? Cosine of u, which is 2 theta, plus, or rather times sine of v, which in this case is theta. Well, so we just applied the sum formula for sine. Now, and in a way, although, don't get me wrong, although this is expanding more terms, this is giving us more terms, essentially we are simplifying our expression. We are simplifying the 3 theta into terms of thetas and 2 thetas. Now, what are we going to do here? Check this out. So we will replace rather this sine 2 theta and cosine 2 theta with the formulas that we just learned in the previous page. That is, we will replace sine 2 theta with, this becomes 2 sine theta cosine theta. Actually, I'm going to highlight different colors so we can distinguish between them. And well, so let me use green for this one. Yeah. All right. And then over here, that's times cosine. All right. Plus. Okay, cosine 2 theta. Okay, how are we going to deal with that cosine 2 theta? Okay, if we recall from the previous page of this handout, there are 3 different possibilities for writing the cosine 2 theta. Okay, let's go back to those formulas. Okay, cosine squared theta minus sine squared theta. 1 minus 2 sine squared theta, 2 cosine theta minus 1. Which one is the best one to use? Well, check this out. Notice our ultimate goal here is to write everything in terms of sines, right? So you might want to use the identity that involves all sines right here, all right? How about that? That's going to be then 1 minus 2 sine squared theta. I mean, you can use your favorite of the 3, but in the end, you will have to keep using the Pythagorean identities to keep rearranging the expression in a way that you end up with terms of sines only. And in fact, these 2 secondary identities, so this is the primary, let me call it 1. Let me call this number 2a and 2b. To label them in a way as secondary identities. Those 2 secondary identities are the result of rearranging this one in terms of by using the Pythagorean identity. So let's use 2a. So this will become 1 minus 2 sine squared theta times cosine theta. All right. Oh, hold on. That's sine theta, right? And let's see about it. Number 1. Okay, yes, I know. Cosine times cosine is going to become a cosine square. How is that going to be all in terms of sine? Don't worry, we'll get there. So that's a 2 sine theta cosine squared theta. Plus, how about we distribute sine times 1 and sine times negative 2 sine cubed. How about we do that? That's going to give us, on the one hand, sine theta minus 2 times sine squared times sine. That's going to give us a sine cubed. Hold on. Yep. Sine cubed. All right. We're getting there. Well, actually, we don't have those. I still need to get rid of this cosine square. I need to take care of that cosine square because notice our ultimate goal does not contain any cosines, and we're going to use a Pythagorean identity, the one that says sine squared plus cosine squared equals to 1. I'm going to solve for cosine to get, that's 1 minus sine squared theta. All right. That's from the Pythagorean identity. Now, let's see. Let's replace with that. And that equals to 2 sine theta times 1 minus sine squared theta plus sine theta minus 2 sine cubed theta. How about we distribute this again? That is 2 sine times 1 and 2 sine times negative sine squared. That's going to give us the following. In other words, that's 2 sine theta is just 2 sine theta. 2 sine theta times negative sine theta. So that's a sine to the first times a sine to the second power. So because we have the same basis, what we're going to do here is combine the powers together. That is invisible 1 plus 2. That's minus sine cubed theta. So we're done distributing this. Now let's just keep carrying the last two terms. That's plus sine theta minus 2 sine cubed theta. And we're getting there, right? Because we may now combine the like terms. That is the sines to the first and the sines cubed. So 2 sine squared. Okay, let me highlight a little bit. The sine to the first and the sine cubes. So, okay, just look at the coefficients. 2 minus 1, or should it be plus 1? No, it's plus 1 actually. And that equals to 3 sine theta. And negative 1, invisible negative 1, minus 2. Isn't that a negative 3? Which one? This one right here? Oh, this one right here? Huh. Oh yeah, that's a 2. Never mind. That's a 2 and that becomes a 4, right? Thank you. And that's what we wanted to show, isn't it? That's the right hand side. Okay. So here is the thing. So in a way we are going to go back and forth between writing trigonometric functions of a multiple angle in terms of trigonometric functions of a single angle that contain powers. All right? So that's one way. That's going into that direction. We can also go the backwards direction by writing powers of trigonometric functions into reducing their powers, but as a price we have to pay for that is to multiply the angle. Well, what am I talking about? Well, let's see. I'm talking about the power reducing formulas. Well, and these identities or formulas here are very, very important when they will be very important in calculus, especially when it comes to solving some problems that involve this kind of trigonometric expressions, for which if we're given, this kind of some kind of problem with a power of a trigonometric function, unfortunately, we wouldn't be able to do anything related to the problem we want to solve. So we need to write these expressions into in a more simpler way. So here is what happens. Power reducing formulas, that's because, well, the power 2 became a power 1, so the power got reduced. All right, hopefully we agree with this. However, the consequence of, as a consequence of reducing a power, it's that this angle gets duplicated here. All right. So we double the angle every time we reduce the power, and this applies to pretty much every setting. For example, let me make something up here. Sine squared, let's say 4 theta. All right. I would like to use the power reducing formula because I don't want that squared. I want power to the first. So that's going to be 1 minus cosine blank divided by 2. Now check this out. And we need to be very careful that because this is a very common mistake when using the power reduction formulas. Again, what happened here? When we reduce the power from 2 to 1, this angle became the double of what it used to be. So if to start with, we have some trigonometric function with a 4 theta, we have to double that angle, and that becomes 8 theta. All right? So it's important to take into consideration these ideas. It doesn't just work for theta to become 2 theta. No, whatever angle you have here, make it double when you reduce the power. And well, that's actually what we're going to apply here for example number 4. So for example number 4, let's see. They're asking us to write an equivalent expression for sine to the 4th power that does not involve any powers of sine or cosine greater than 1. Just powers of 1. But hold on. This is sine to the 4th power. We don't have formulas for sine to the 4th power. We have formulas for sine to the 2nd power. Well, check this out. This is the same as saying this sine to the 4th theta. It's the same as saying sine squared theta quantity squared. Do we agree that the power 4 can be rewritten as a power of another power, multiply the powers, and that's a 2 times 2? So that's how we're going to start. And then from here, we're going to make our way through reducing the powers. So number 1, check this out. So this sine squared right here can be replaced with this expression right here by replacing sine squared with, whoops, so that'll be sine squared becomes 1 minus 2, 1 minus cosine 2 theta, the whole thing divided by 2, quantity squared. Okay, that square outside of the parentheses is indicating that we need to square both the numerator and the denominator. For the squaring of the numerator, just leave it like that for now. That's simply 1 minus cosine 2 theta, the whole thing quantity squared, and 2 quantity squared, that becomes a 4. All right, we will deal with the numerator shortly. Now, my advice for when dealing with these kind of problems, well, how about instead of writing this over 4, write it as 1/4. Trust me, it's going to be a lot better. So we may now go about expanding the binomial squared. And well, in this case, you can do it your favorite way by writing this as 1 minus cosine 2 theta times itself and foiling, or using the binomial square formula that I have been used throughout the semester. That's a plus or minus b, quantity squared. That's a squared plus or minus 2ab plus b squared. Depending on whether you have a plus or a minus, well, just take the plus if it's a sum, if it's a sum for a binomial, or take the minus if it's a difference for the binomial. All right, so in this case, since we have a minus, I'm going to use the minus version. So that equals to 1/4 times the result of expanding this binomial, that is 1 quantity squared, which is 1, and then careful, minus 2 times the quantity A and the quantity B, so A is 1 and B is cosine 2 theta. That'll be 2 times cosine 2 theta. And plus the quantity B squared, that's cosine squared 2 theta. How careful with that. All right. So we're done with expanding the binomial. How about now we distribute the 1/4, because what's going to happen here? So we're not done. We only have half of the problem solved, because, well, we started with a power 4 for sine. However, we need to take care of this cosine squared using the power reducing formula a second time. But first we need to distribute this 1/4 so we can deal with this separately and leave these other two terms alone. Alright, so that's 1/4 times 1, which is 1/4. 1/4 times negative 2 cosine 2 theta, but check this out. 2 times a fourth is the same as 1/2. And 1/4 times cosine squared, that's simply 1/4 cosine squared 2 theta. Alright, let me do another highlight here. How about we replace this cosine squared 2 theta with the identity that we have over here. And now, as a pattern recognition, both formulas look almost the same. Involves a 1, a cosine 2 theta, and a division by 2. However, the power reducing formula for sine has a minus in between, and the cosine function has a positive sign in between. That's a way to distinguish between the two. The reason why I mention this is because, well, when you get tested on this, you will be expected to memorize these formulas, all right? So just keep that in mind. So same formula, they just differ by the sign in between. But well, what if I put the negative signs reverse? I mean the signs reverse, like a plus here and a negative there. Well, another way to relate this, if it works for you, well, remember even in odd properties of sines and cosines. Well, sine, it's an odd function, so if we evaluate it at a negative angle, we get the negative outside. What about for cosine? That's an even function, that becomes positive, right? So that's another analogy, if we will, or another way to relate with other properties that we know, even though here we're not using those properties. All right, so let's keep going with this 1/4. 1/4 rather, minus 1/2 cosine 2 theta plus, careful, 1/4 times the result of using the power reducing formula for cosine squared 2 theta. And we need to be very careful here. Number one, we're going to use the formula in green, 1 plus cosine 2 theta, the whole thing divided by how about 2, right? And I made a mistake on purpose here to see if you can catch it. What's the mistake? It should be a cosine 4 theta, right? Remember, if we start with a different angle, every time we use the power reducing formula, we have to double the angle we start with. So in this case, we started with 2 theta, that has to become a 4 theta. Careful with this, right? Actually, let me do a second highlight. I know it's going to look a little weird here. Two colors overlapping. Let me do. Just so it makes more sense, right? All right. Let's see. Number one, how about we multiply the 1/4 with the 1/2? Well, where's the 1/2? The denominator, so that's going to be 1/4 minus 1/2, and that's what's that? A cosine 2 theta plus 1/8 times 1 plus cosine 4 theta. All right. That way, so we can just easily distribute a 1/8 instead of distributing a 1/4 over a 1/2 and another 1/2. All right, let's go for it. That's 1/4 minus 1/2 cosine 2 theta plus 1/8. So the 1/8 times 1 is just 1/8, and the 1/8 multiplying with the cosine 4 theta, that's 1/8 cosine 4 theta. All right. How about we combine like terms? I'm talking about the constant values. That is, how about LCD? So we can combine 8s with 8s. That is, 2 8s plus 1 8. Isn't that a 3/8? When we combine these two together, that is this one plus that one. And that's minus 1/2 cosine 2 theta plus 1/8 cosine 4 theta. And that's the final answer. And as we can see, that final and that expression we obtain in the end, it meets the requirements here. That is, number one, does not involve any powers of sine or cosine that are greater than 1. Only powers of 1. However, it doesn't matter the multiples of the angles, because that's how the power reducing formulas work. All right? All right, how about the half angle formulas? Well, these are the formulas right here, and well, actually these formulas are the result of playing with the power reducing formulas. By the way, there's a little typo here. This should be half angle. All right, so check this out. Remember how, let me show you just one formula. Remember how we started with sine squared theta equals to 1 minus cosine 2 theta over 2. Right? That was the formula to begin with. Let me change color here so it doesn't get confused with the work we did before. All right. Again, check this out. We did something like, we did this. What about sine squared of 6 theta? Let me make something up, right? Something new. That should be 1 minus cosine of, isn't that? Well, we have to double that angle. That has to be then, that becomes a 12 theta. Okay, 12 theta. And the whole thing divided by 2. All right, we can have multiple angles, of course. However, we can this also works for fractions of angles. How about, check this one. How about sine squared instead of theta? How about I do theta over 2? All right, that's going to be 1 minus cosine. Oh, careful here. So every time we use the power reducing formula, we have to double the angle. However, what is the double of theta over 2? Or in other words, what is the double of a half? What's that? Oh, okay, so I can't hear you, so theta, just theta, right? So, well, I'm going to take the square root here. Sine of theta over 2 equals plus or minus the square root of 1 minus cosine theta over 2, which is this formula we have here. I have it in terms of alpha, but it's the same thing. You can use your favorite letter, alpha, beta, gamma, theta, phi, whatever. Doesn't really matter. In a similar way, using the power reduction formula for cosine, we can get this formula, and the same way for the tangent of a half angle. Either way, we can get the same thing. All right. How about we use these formulas to find the exact values for, okay, perfect. The exact values of cosine of 15 degrees and sine of negative pi over 8. Alright guys, so check this out. We already did the first exercise, cosine of 15 degrees. We did it last time. Well, last time we did review, last week. However, we did it using the sum and difference formulas by breaking up the number 15 as a cosine of 45 minus 30. Alright? However, we're not going to do it this way this time. We're going to use the half angle formula. So, we're going to write this like cosine of 2 times, 1/2 times what number equals to 15 degrees? What's that number? What was that again? 30, all right? Loud, don't be shy, come on. All right, so this means we're going to use the power, the half angle formula for the cosine function. However, be careful about how we report these results, because coming back to the formulas, there's a plus or minus involved right here. We're not going to report 2 results because the cosine of 15 degrees has to have only 1 result, not 2. And well, in this case, we need to take into consideration the quadrant in which this 15-degree angle is located at. And that is the first quadrant. Do we agree with this? That means all functions in the first quadrant are positive, so for that reason, we will just take the positive version of it. And that's 1 minus cosine of, in red, just so you can connect this, 30 over 2. How about we compute this? Cosine of 30 degrees, isn't that 1/2, I believe? 1/2? No, it's not 1/2. It's root of 3 over 2, right? Okay, big radical. I'm going to need a really big radical. So that's going to be 1 minus root of 3 over 2. The whole madness here divided by 2. Okay? I know these numbers are going to get a little funky here, but that's what it is. It is what it is, right? Well, so I know. To make our lives a bit simpler into reading these numbers, especially the radicals, how about instead of dividing this by 2, how about multiply by 1/2? That's going to look a lot more friendly, trust me. That's a 1/2 times 1 minus root of 3 over 2. And I think you know why am I leaving some space over here. That's because 1 over 1. And how about multiply by 2 and divide by 2? That's so we can combine the 2 fractions together inside of this. Yes. Which one? Yeah, that's what I meant actually, right? Thank you. Thank you. Yeah, some collateral damage, right? Yeah. So that's the square root of 1/2 times. Okay, that's 2 halves plus root of 3 halves. Well, that's simply 2 plus root of 3 over 2. Now, multiplying across, 1 times this 2 plus root of 3 will simply be 2 plus root of 3 in the numerator, and 2 times 2 equals to 4. And we're almost there, except that how about we simplify the denominator, because the number 4 happens to be a perfect square, and the square root of 4 is 2. And the numerator, just leave it the way it is. Final answer. All right. And that's the type of answer we are expected to submit both in the ALEKS homework and as well as on the exam, because no decimals unless otherwise specified, right? We could use these decimal answers. All right, what time is? Oh yes, we can sure go about the next example. Okay, so we are to evaluate sine of negative pi over 8. Negative angles. How about we use the even and odd properties of trigonometric functions so we can proceed using the formulas. Okay. Recall that the sine function is an odd function. That is, that if we evaluate the trigonometric function at a negative angle, that sine goes outside as a negative sine of pi over 8. All right. What about it? So we may now easily use the, what's it called, the half angle formula here. So let's see. Let's see if we can get the angle here. That's negative sine of 1/2 times what equals pi over 8. What's the mystery number here? Pi over 4, right? Pi fourths. All right? So now, in this case, okay, let's ignore this negative sign right here. All right? Okay, the angle pi over 8, again, it's an angle that lies in the first quadrant, right? So, how about we use the positive formula, that is 1 minus sine of pi over 8, oh no, not pi over 8, pi over 4 over 2. But it's, in this case, yes, this negative sign, it's not coming from the fact that we're working on an angle that lies on another quadrant where the sign is negative. No, this negative comes as a result of using the even and odd identities here. However, if we use this negative pi over 8, that is an angle in the fourth quadrant, well, that would have been the reason why we would get this negative from the formula instead. So let's see. So that's pi over 4. And what sine of pi over 4, if I'm not mistaken? That's 1 minus root of 2 over 2 over 2. And let's keep going with this. Write it in a friendly way. That's negative 1/2 times, that's a 1 space, root of 2 over 2. Okay, you know what's that space for? That's 1 over 1, 2 times 2. And that's a negative, the square root of 1/2. And that's 2 minus root of 2 over 2. And well, as a pattern recognition, hopefully you can see that we are going to do a very similar calculation like we did before. So that's the negative, the square root of 2 minus root of 2 divided by 4, and simplify the number in the denominator taking the square root. So that's the square root of 2 minus the square root of 2, the whole thing over 2. Final answer, and I think this is a good place to quit today.